Welcome back, everybody, to the conference on categorical probability theory for the final day and the first session. And our first speaker today will be Alex Simpson, and he will be talking about synthetic probability and will hopefully teach us about random variables. So I'm very excited about that. Alex?
Okay. Thank you very much, Arthur. And while I share my screen, which will just take a few moments, I need to make sure I do the right one. Let me thank the organisers for this opportunity to speak. I've found it a very stimulating conference so far. Let's see if I click that. Can you see my slides?
Yes.
Yes. Okay. So I'm going to be talking about synthetic probability theory, what I call synthetic probability theory. We've already heard quite a few talks that have used the words synthetic probability theory. So I thought I should start by firstly explaining in what sense I'm using the term synthetic probability theory. So this is synthetic probability theory in the spirit of other synthetic subjects going back at least to synthetic differential geometry that share the property that they're essentially derived from having models that are toposes, and in those models one sees principles governing the subject that you're looking at, so differential geometry in the case of synthetic differential geometry. But as Spitters in his talk yesterday mentioned also synthetic domain theory and synthetic topology, which is what he was working with. There's also, for example, synthetic differential topology, which there's been a recent book about. So there are all these subjects, and kind of what the use of the word synthetic here is essentially derived from the synthetic analytic distinction in philosophy. There's not going to be much philosophy in my talk. I just want to mention this briefly. So the idea is that one is being synthetic in the sense that you're axiomatizing contingent facts about the subject that you're looking at, in my case, or in our case, probability theory, in the sense of how you experience that subject, rather than doing the analytic approach, which in the case of mathematical subjects tends to be that you define the concepts in something like set theory, and then you prove results as necessary consequences of your definitions. So in this sense, synthetic probability theory that I'm doing is, I think the synthetic probability theory that other people have talked about based on Markov categories perfectly well fits into this picture too. But where there's a big difference is in the next point. So one of the main goals of what I'm doing today is to provide a single set of axioms, essentially, that allows us to develop the core constructions and results of probability theory and essentially derive all of probability theory. I didn't dare put that on the slide, but I don't mind saying it live. I do actually know some limitations of what I'm going to say, so it's not really all the probability theory, but a great deal. And this is very different from the kind of axiomatic approach in Markov categories, where you take sort of probability theory one concept at a time, as it were, and for each concept look for the appropriate structure on the category. Okay, so the way I'm going to approach things in this talk is, so that this might sound rather complicated to lots of people, especially mentioning toposes. We had lots of toposes yesterday. Hopefully don't be too frightened, because I want to kind of adhere to the last point here, which is what I believe, and the point of view from which I'm going to give this talk is that I think the approach has the potential to provide a simplified approach to probability theory. So probability theory, a lot of nice concept in it, but when one develops it rigorously, it's rather mathematically complicated, and perhaps more complicated than it really needs to be. So to approach this point, I want to go back to what I said here about we've got the synthetic versus analytic approach, where in mathematics, the analytic approach would be deriving theorems from set-theoretic definitions. And as I said these maybe have a tenuous relationship to the concepts they're formalizing. So in the case of probability theory, I'm not the only person that thinks that. So here's a nice quote from Giancarlo Rota, who wrote a very stimulating essay called 12 Problems in Probability Theory that no one likes to bring up. And he observed that in mathematics, the definitions that one bases one's theory on are very often misleading, but perhaps in probability theory, the initial definitions one start with are even more misleading than in other mathematical subjects. So what's a good example of like one of the first definitions one starts with in probability theory? Well, of course, probability theory as a real mathematical subject so starts with random variables. Of course, you need some definitions before you get to random variables. You need sigma-algebras, probability measures, measurable functions, and so on. But probability theory as a real subject starts with random variables. I've got what a random variable is on the slide. I don't really want to talk you through it. Paolo did a very good job in his talk of explaining the notion of random variable. Like in Paolo's talk, I'm going to, when I say random variable, I mean essentially a random element in some space. A doesn't need to be the real numbers. And importantly, such random variables are given by maps from a sample space, which is a probability space. And the point I want to make about this is that in probability theory, the sample space has a very ambivalent status, in the sense that if you're doing probabilistic arguments, it's not considered kosher to refer to elements of the probability space, except that in certain circumstances you apparently really have to. So there's this sort of ambivalence here in the probability space. You'd like to pretend it's not there, but sometimes you really need it. Okay, so the definition of random variable, in my view, it's a very, one gets a very long way with probability theory. It's a beautiful subject, but it's a very complicated definition. And it's not just me and Giancarlo Rota that think so, but here's another quote from David Mumford, a Fields Medal winning mathematician who wrote a rather provocative essay called The Dawning of the Age of Stochasticity. And he observes in that essay that, of course, the basic object of study in probability is the random variable, and it's rather complicated as defined, so perhaps one should treat it as a basic construct. And he says it's artificial and unnatural to define it in terms of measure theory. So in this talk, I don't really have any axe to grind against measure theory. Measure theory is a very good subject, and if one's dealing with probability theory, there's no avoidance of talking about measures. We're certainly going to do plenty of talking about measures, but rather it's the issue of defining the notion of random variable in terms directly as a definition of mathematical structure, as a mathematical structure based on measure theory. So what could one do instead? Well, actually in this article, Mumford has some proposals. I'm not going to follow his proposals. They're not very well worked out. What I'm going to do is what makes sense in the topos I have, which I'm going to keep completely in the background of this talk, but it's derived from a model, what I'm going to do. But the idea is very intuitive, and it's an idea that I think should find sympathy in the category-theoretic audience, because it's basically the idea that when you talk about a concept, that rather than giving it an implementation by giving it a concrete set-theoretic definition, you rather axiomatize how you're going to use the concept. So when one defines a notion in category theory via a universal property, that's an instance of this approach. Of course, random variables are rather a complicated notion. I think they're much too complicated to deal with by a simple universal property, but still I'm going to follow the basically the same idea, that we axiomatize random variables in terms of how we use them, rather than in terms of giving a particular implementation of what a particular concrete definition of what they are. And I just want to make a connection with computer science here, because this is what people often do. In computer science, when you're defining notions of data type, we have in computer science something called an abstract data type, where you have an interface that presents what you can do with the abstract data type, but you hide from the user the way it's actually implemented as a mathematical definition. Okay, so I'm going to do that. I'm going to axiomatize random variables in terms of how we use them. The basic setting I'm going to leave rather up in the air. You can choose your favorite one of these. We're going to work with sets. So, but by sets, you can understand the objects of a topos from the viewpoint of the internal logic. You can understand a universe of sets in extensional type theory, if you like, or you can understand sets in a more Zermelo-Fraenkel-like set-theoretic sense, except I don't want to say that everything in the universe is a set. But anyway, we're just going to work informally with sets, and importantly, my underlying logic is going to be classical. So I'm going to just do ordinary classical reasoning with sets. But I'm not going to assume the full axiom of choice. That's going to be crucial, but I will allow the axiom of countable dependent choice. So we can define a sequence by making a countable sequence of dependent choices. So in a sense, I'm using, by axiomatizing probability theory in sets, I'm sort of doing something rather similar to Bas Spitter's yesterday, except that in his setting, the logic most definitely was not classical and he didn't have any form of choice. So things are going to be much more familiar in my setting because we've got more familiar classical set theory with quite a lot of choice around. And importantly, going back to the idea that I think I'm presenting a somehow simpler notion of probability theory, I'm going to try and make things as the axioms as simple as possible from the point of view of probability theory. So I want to avoid fussing over issues that one would rather not fuss over in probabilistic arguments, such as, in particular, issues regarding measurability of things.
Alex, we have just a short maybe question. What does dependent choice means and how is it related to dependent type theory?
So it's not really related to dependent type theory. It's rather that if you have, if you make a sequence, if you've got a sequence of things that given x0, then there exists an x1 with some property, and then given x1, there exists an x2 with some property depending on x1, and then given x2, there exists an x3 with some property depending on what you've had so far, and so on. You can wrap all these countably many existence things into a sequence that gives you the x0, x, or whatever I started with, I don't remember, x0, x1, x2, x3, all satisfying the properties. So you're making existential choices along the way. You've got countably many of them, but each one depends on the previous choice. So it's countable choice, but with dependency between the successive choices. Yeah, thank you for the question. Okay, so let's start axiomatizing the properties of random variables. And now, to many people, they're going to feel that I'm presenting things rather slowly, but I think it's appropriate to do in a general conference. And the idea is that I'm going to say the general principle first. I'm then going to axiomatize it set theoretically, and then I'll show that actually there's a very succinct way of saying what we've done category theoretically. So the basic idea is we've got random elements or random variables taking values in a set A. So I'm just going to say for every set A, we have a set of random variables that have values in A. And if we have a random variable and we have a function from X in A, and if we have a function from A to B, then, well, if I can get a random element of A out of X, then once I've got that element, I can apply F to it. And doing that is tantamount to giving myself a random variable in B. Naturally, if you use the identity function here, you preserve X, naturally composition would work like this. So we're basically saying we have a functor that gives us random variables. Notice there are no measurability assumptions. This is for any set. We don't want to assume a set with a sigma algebra or anything like that. We want to avoid fuss. Maybe I'll just click over to my notes here.
Alex,
So
Alex, question.
Yes, okay.
When you say RV of A, do you assume that they all have the same sample space or random variables?
Very good question, because I just happen to have switched to this slide, to the board here, where we have a sample space in it. So random, one can think of, to begin with, random variables of A as functions from choose a nice sample space that you like. and it's functions out of that fixed sample space. But in the end, we're going to see problems with this intuition. But the other way, I mean, I'm going to keep on going back to this analogy because most people here have been indoctrinated with the idea that random variables need to have a sample space. So we'll come back to explain what's going on in sample spaces. But I also like you to try to get to part of your brain that doesn't know about sample spaces and believes that random elements can exist as a primitive concept. And in that setting, we're never going to talk about sample spaces. So if I go back to the slides here, so this just makes sense from the notion of a random element in some sense. So the next axiom says, well, so we do need some measure theory. It's very natural to have that. So if we've got a random variable, we want to talk about probability. So every random variable is going to have an associated probability law. It's distribution, or law, as it's called. And for me, I don't want to fuss over measurability. So a probability law is simply going to be a probability measure defined on the full power set of the set. So for every subset of A, we have a probability, and that satisfies the usual countable additivity properties of a measure. And for those in the know, we didn't want to have the axiom of choice in order to be able to get a long way with power set measures. If we had the axiom of choice, then power set measures would be problematic later on. But we don't need to worry about that now. So measures are simply measures on the power set. And moreover, a probability law, well, if we've got a random variable x, and we've got a function that, it's a random variable in the set A, we've got a function that takes us from A to B. Well, if we transfer that probability, if we transport the random variable x along f, then of course the induced probability law, from the idea of just how we transport a random variable, the induced probability law should be the push forward of the probability law of x. So we have that as part of the axiom. But in fact, this set of power set defined probability measures is a functor on the category of sets, with push forward as the functorial action. And these two axioms are just saying, so again, we have a very succinct category-theoretic formulation that we have the probability law is some extra structure we have, which is a natural transformation from the random variable functor to the probability measure functor. Okay, so just with this structure, we can already define those concepts of pertaining to random variables that essentially deal with probabilities, the probability laws of random variables on an individual basis. So we can define, it's important to remember this notation. I'm going to use it a lot through the talk. So this is my notation for two random variables being equidistributed or identical in law. Those are two ways of calling this notion. So that's just if they have the same law. And for example, we can define for a random variable its expectation as the integral, if it's a real valued random variable, as the integral of the identity function with respect to the probability law, as long as that's finite. And if it is, we say that it's integrable, and the value of the integral is the expectation. And of course, we can define other similar statistics like, other than expectation, like variance, like other higher moments, and this kind of stuff. The integral makes sense just by the general theory of integration here, of Lebesgue integration with respect to measures. Okay, so that's about individual random variables, but the whole point of random variables, as was nicely emphasized in one way in Paolo's talk, is that random variables are a very good formalism for talking about joint probability laws. And to talk about joint probability laws, well, so I already apologized for going through the axioms maybe slowly, but actually this one I normally do in several pieces, but I'm just going to put everything together here. So the idea here is that if we have a finite or countably infinite family of random variables, then giving such a thing is equivalent to giving a random family. So let's think of the example of a pair. That's a family with two elements in it. So we've got two random variables, x1 and x2, perhaps taking values in different sets. then having that pair of random variables together gives you a random variable into the product set A1 times A2. Because you've got random elements, you can essentially think of choosing the two random elements at the same time. If we go back to the idea that we're thinking of the random variable set as like the function space out of the sample space, we're saying, well, we're observing that this preserves countable products. Of course, it preserves arbitrary limits because it's a right adjoint, so at least it preserves countable products here. Okay, so if we go back to the slides. Okay, so if we have a countable family of random variables, so that's a family of elements, each xi is from the set, is a random variable in AI, we can also view that, and I'm just going to use this notation here, I'm going to forget that category theoretically there's really an isomorphism between these two sets. We can view such a family of random variables as itself a random variable on the product space. Okay, that's just a notational convenience for what comes later. So having done this, we now got a way of talking about joint probability laws. And we can define notions that depend on joint probability laws. So for example, if you've got two random variables, well, they are independent if for all subsets, because we're not worried about measurability, the joint law of them assigns to the rectangle that what we get from producting by the marginal laws. It follows from the functorial properties that we've had before, that when you've got the probability measure with the joint law here, that the px is the marginal for the joint law here, and py is the marginal for the joint law. So it's the usual definition of independence between two variables. One could define independence between n variables in exactly the same way, quantifying over subsets of the n different spaces. Alternatively, mutual independence can be defined inductively using binary independence, as is well known. And then infinite mutual independence is just mutual independence up to, well, for any finite number of factors.
Alex, may I ask a question?
Yes, who's that?
This is Tom Leinster.
Yes, hi, Tom.
Hi. Your notation, I greater than or equal to 1 indicates you're only thinking about countable families here, or is that correct? On the left-hand side, you have...
Oh, right. So actually, this definition one could perfectly well define also for uncountable families.
Okay, great.
I was indeed only thinking about them, but there's nothing on this slide that requires that. The only thing is, if we have an uncountable family, we don't know that we've got a probability law for the whole sequence, for the whole family, because the preservation of products is only for countable products.
Okay, thank you.
Yeah, okay, thanks for the question. Okay, so now we're going to get to what I think is quite an interesting little law, which is very useful. And this, here I want you to think about random variables in some intuitive sense of a random variable defines a random element in its space. And so this axiom says if we've got a random variable y that taking values in B, and if we've got a subset of B that has probability 1 and the law of y, so that means y is almost sure to end up in B, then it's a rather natural concept to think of, from this point of view, from this axiomatization, it's rather natural to think of, well, in that case, since y basically lands in A, we should have a random variable in A given by y. The natural way to say that is there is a random variable x, that's valued in A, that gets transported under the inclusion function to x. And it turns out, as we shall see, that the axiom just says there exists one, and it turns out, as we shall see, that there, in fact, if we have that axiom, then the x is necessarily unique. And the reason for that is because this axiom gives this what I think is a very nice extensionality principle. So it turns out that with this axiom, equality of random variables coincides with almost sure equality. So that's formulated in this proposition. So if we've got two random variables x and y, then the probability that they're equal in their joint distribution equals 1. Now this is kind of the usual standard informal notation, which I'm going to use whenever possible now because it's easier to read. But just to say how one gets this informal standard notation from the definitions I've had before, that where the probability law is always associated with a particular random variable. So to say the probability that x and y is 1, we're saying the probability of the joint law, according to the joint law of x and y, of landing in the diagonal set in A times A is 1. Okay, so that would be the official way of writing it. So there's always this issue in probability theory that you define random variables as functions, and then you have the notion of almost sure equality and lots of definitions. As I think Paolo emphasized in his talk, they only define random variables up to almost sure equality. So one's all the time reasoning with almost sure equality, and you have to kind of, well, you know that you can basically treat it as if it's equality, but here we can certainly treat it as if it's equality because it actually is equality. And it follows from this that, well, one way of saying this I don't want to dwell on, which is the random variable functor preserves monomorphisms, and from that the existence of the restricted random variable x in the restriction axiom on the previous slide follows. I'm actually going to, it's very short, I'm going to give you the proof of extensionality, but before doing that, let me go to my notes here, because we need to make an adjustment to our idea now. That so actually random variables in the set in A, we're now thinking of are not actually functions, but we're quotienting that by almost everywhere equivalence. Okay, there's still an approximately equals here because we're going to have to depart from this later, but let's go back to the talk. So I do want to give you the proof of this. So the interesting direction is that if two random variables are almost surely equal, then they are equal. So as I said, almost surely equal means the probability of x and y landing in the diagonal in A times the diagonal set in A times A, according to the joint law of x and y, that probability is 1. So suppose that's the case. Well, because the diagonal is then a subset of A times A of probability 1, by the restriction law, by the restriction axiom, we can restrict the joint law xy to a random variable z valued in the diagonal set. That gets transported to the pair xy. So once we've got that random variable z in the diagonal set, well, we consider transporting it by I and then following that by the first projection, and transporting by I and following by the second projection. So transporting by I gives us xy, and if we project xy, and if the random variable xy, and if we project out with the first projection we get x and the second projection we get I, but of course these two functions here are equal because we started off in the diagonal set. So x equals y. Okay, so very simple argument, but a nice consequence because now we can do probability theory with the correct notion of equality between random variables, as it were. And
I have a question.
This later, yes?
So from the restriction axiom, wouldn't you get I of z equals d?
Sorry, D is a set, not a random variable. D is the subset of the diagonal subset of the set of pairs from the set A times A, the set A squared. So it's the diagonal in A squared.
I see.
So we restrict, the restriction axiom says we can restrict a random variable to a measure one subset. D is the measure one subset. X, Y is the random variable we're restricting, and so Z is the restricted version of the random variable, and it gives us back the random variable we restricted. I think we should take this offline. I'm sorry, maybe I'm going a bit too far in some ways, but I think, yeah. So just to say, this was the first axiom I didn't give a category-theoretic formulation of the restriction axiom, but in fact it has a perfectly nice category-theoretic formulation, which is that we've got the naturality, the probability laws, they're a natural transformation, and it's simply saying that certain naturality squares are pullbacks, namely those where you have a mono here. Actually, the naturality law, the restriction axiom, as I formulated it, said it's a quasi-pullback or an epi-pullback, as it's called, and then it follows from that that it's in fact a pullback. That was the restricted random variable is actually unique. But never mind, if one wants to have a nice category-theoretic axiom, one might as well just say it's a pullback, because that's going to follow anyway. So we have a nice category-theoretic formulation of the restriction axiom, and it follows from that that the real variable, the random variable's functor preserves equalizers. So in fact, it now preserves all countable limits. Okay, so as we've done things so far, we've been talking about laws of random variables, and so properties of random variables, but we haven't actually met any random variables. So do the axioms tell us that some interesting random variables exist? Well, because we're preserving the terminal object, that's part of preserving countable products, we do have Dirac random variables. So for any set A and element X of the set A, there is a unique, as it turned by the almost sure equality being actual equality, there's a unique random variable delta X that has the Dirac distribution. So essentially it's the probability distribution that has probability 1 of being the element X. Of course, those are not very random variables. And in fact, we can't do better than that with the axioms we've got so far, because all the axioms we've got so far are consistent with the with the random variable functor being the identity functor. So we want something more interesting than that. And the natural thing to do is to give us the simplest actual random thing we can think of, which is a fair coin. So my next axiom is just going to say there exists a random variable valued in the 2-element set. So 0 is nice and round, so that's heads. 1 is kind of long and thin, so that's tails. And the probability of heads and the probability of tails are both a half, because it's a fair coin. But if we've got one fair coin, well, of course, often one wants to talk about having lots of fair coins, all independent from each other. So how are we going to get some independent fair coins? So the next axiom, so we need another axiom now, is a very important one. And this is saying for any random variable that we've already got, X, and for any other random variable that we want to now make things independent of, Y, doesn't need to be over the same set as X, we can find another random variable that has the same law as X that's independent from Y. So now, if we go to our heuristic here that random variables should be like maps out of a fixed sample space, we now find that we have a bit of a problem with our fixed sample space, because there might not be room in the sample space to find a new independent copy of some particular random variable we've already got. So in general, like probability theorists in this situation, they would extend the sample space by having some larger sample space that projects down to this one. So now things get a bit hairier from the sample space point of view. You can still bear in mind this picture if it's helpful for you, and just think of the sample space has to have enough room in it to mean that you can always find independent random variables. There are ways of making that precise, but I don't want to go into that here. So, but we'll just take this axiom at face value. And one thing that's nice about it is it gives us very simple constructions of things we'd like. So here's a proposition that's very useful in probability theory. For every random variable, we can find an infinite sequence of random variables, all independent and identically distributed to the original random variable X. So something that's used all the time in probability theory. IID sequences of random variables are very common, pervasive in probability theory. So let's prove this. It's like a 3-line proof. So we can start with x because there's no problem using x for the first one. We just need to find lots of independent copies of x. And inductively, whenever we've got the previous many random variables, then the independence axiom on the previous slide gives us the next random variable xi that has the same law as x, and we just make it, we could change the y that we're making things independent from in the independence axiom, so we just make it independent of everything we've got before. It's a 3-line, well actually that is already 3 lines as written, but it's kind of morally 2 lines. So there's another line in the proof because we then observe that actually we need to use, this is a case that we need to use dependent choice, because here we've only got existence on each case. We don't have any sort of canonical xi that satisfies this. So we get the required sequence in the end by dependent choice. So very simple construction of something that's used in probability theory, and a nice synthetic argument. And by this proposition, we can specialize x to our fair coin. And of course, we now have an infinite sequence of independent random variables, all identically distributed to the fair coin. So something that's very well studied, and we have the usual laws of large numbers. So I don't want to talk you through these. I mean, if you know them, then they're what you expect. If you don't know them, this isn't the place to learn them. It's just saying that on average, the number of coin tosses tends to a half in 2 different strengths. The point I want to make is here I'm using the standard informal notation. So here we've got a limit of probabilities of approximating sequences tending to a half, being close to a half, tending to 1. And here we've got the probability that all infinitely many coins converge, land in a sequence that itself has the property that the averages tend to a half. Actually, I said I wasn't going to tell you what the laws are, but I've just kind of described them rather quickly. The point is that if we want to translate this to our official notation, the P's need to be laws associated with random variables. This law, each time we use a P, we only have finitely many variables inside. So it's the law of, for each n of the variables k0 up to kn minus 1 or something like that. Or yeah, k0 up to kn minus 1. So it's a law of a finite sequence of random variables. This one is really talking about a law of an infinite sequence of random variables. So this is the first time that we use the axiom that the random variable functor preserves countably infinite sequences. So that's, we're preserving countably infinite sequences to define a probability measure on then the set of infinite sequences of coin tosses, of heads and tails. So the usual uniform probability measure on Cantor space.
I had a question about that second limit. What does this look like? You have a limit of elements in a fixed set, or you're changing your set A as well?
Sorry,
the random variable.
So each ki is a random variable, is just a coin, a fair coin, and that evaluates to 0 or 1, and we're simply evaluating sequences of zeros and ones. So this is a random variable that is either 0 or 1, and we're averaging the first n zeros and ones and seeing if it's close to a half. But the probability, well, actually we're saying that this sequence of averages is actually a convergent sequence and is equal to a half. It's the usual strong law of large numbers, but this isn't really the place to go into it in more detail. So I'm very behind time. So I just need to think how to do things. I think I will talk about this. So yeah, so we've got a measure now, a probability measure on infinite sequences of coin tosses. We want that measure to be nicely behaved. And this is the only place I need to use somehow sigma-algebras. And I'm not really using sigma-algebras as an abstract notion, but rather I'm using the fact that this is a nice space. It's a standard Borel space. Cantor space is a standard Borel space. And that the sigma algebra of Borel sets is a very natural mathematical sigma algebra of nice sets here. And what I want to say is that whenever we have a measure that's the probability law of a random variable on such a nice space, a standard Borel space, then so our probability laws are evaluated on all subsets, and for any subset, there exists a Borel set that has null symmetric difference in our probability law on all subsets from that arbitrary subset. So every subset is close in our probability measure to a Borel set, so 0 distance from a Borel set in the natural metric on subsets. Sorry, maybe not metric, quasi-metric or something. Anyway, so this would follow, actually, if we had a very strong axiom like all subsets of reals are Lebesgue measurable, which is known to be a consistent set-theoretic axiom modulo some assumptions, but I prefer this axiom because those assumptions about inaccessible cardinals and things, I believe, are not needed for this axiom here. It's a bit weaker than asking all sets to be what's called Lebesgue measurable. And from this axiom, I just want to say this: it follows that the measure we have on Cantor space is translation invariant in the appropriate sense. Okay, so I think I have 5 minutes of time according to the proper schedule. I've had a few questions, so I might just a little bit overrun. I'm going to be a little bit selective of what I talk about. I think I'll start with this. So when the next progression beyond what we've done so far in probability theory, almost everything else in probability theory depends on the notion of conditional expectation. And one can already see that this is going to be sort of propose a challenge in this setting, because the standard kind of powerful notion of conditional expectation one uses in probability theory is you look for the conditional expectation of a random variable with respect to a sub-sigma algebra of the underlying, of the sample space you've got for the random variable. And then such things are characterized by such conditional expectations, they're characterized up to almost sure equality by the various characterizing properties that include measurability with respect to the sub-sigma algebra. So we're trying to avoid sigma algebras, and we don't want to fuss over measurability, as I said, but even more fundamentally, we don't have a sample space. So how are we going to deal with this? And so how are we going to deal with this? Well, actually, I'm going to deal with it by just restricting to a very common situation in which one uses conditional expectation, which is just conditioning one random variable with respect to another random variable. Now, in probability theory, it's thought of that this isn't really general enough. One really needs this extra generality. But in our setting, because random variables can take values in very complicated sets, actually this turns out to be much more powerful than it is in probability theory. So in our setting, I'm saying this is general enough. It's been general enough to do everything I needed to do so far. So we do that. We just condition random variables with respect to other random variables. That's very intuitive. Then we need to worry about the measurability consideration. And it's a very natural concept to replace this. And that's something I know from database theory, which is the notion of functional dependency. And the way this works in our setting is that we say a random variable z taking values in B is functionally dependent on a random variable y taking values in A. Notation z is functionally dependent on y. If there exists a function from A to B such that you can transport the random variable y along f and get z back. And because of our identification of random variables up to almost sure equality, you can understand this as saying sort of f maps A to B in such a way that almost surely the law of A, well, sorry, the law of A is, it's not to do with the laws, but almost surely the values of the random variable y are transported to values of the random variable z. And then the definition of conditional expectation is just the usual one. The second part is just the usual one. I don't want to go over it now. But the measurability assumption, so this would normally be that z is f measurable on the previous slide. is now replaced by Z is functionally dependent on Y. And to my way of understanding things, this is a kind of very intuitive way of formulating the conditions. I mean, conditional expectations always take a bit of getting your head around, although if you have Paolo to help you with a map of America, it's actually can be a lot easier. But anyway, here one doesn't need to worry so much about understanding the measurability condition because it's been changed to functional dependency. And rather systematically, in probability theory, measurability conditions with respect to sigma sub-algebras of the sample space can be replaced with functional dependency conditions. And there were going to be lots of examples of that later in the talk, but I just want to flash a few things. So from conditional expectation, one can define conditional probability in the usual way. This is our last axiom, so I might as well do this in detail and then just flash up the highlights from the rest of the talk. So the last axiom is saying that actually I want to be rather careful what random variables I have. So I'm not saying in particular that any probability measure gives me a random variable. Rather, the flavor of this axiomatic approach is to give you different constructions that preserve random variables. That's what we've been doing so far. And in fact, these constructions are all consistent with that every random variable is obtained as a push forward or transport of a random variable on Cantor space with the uniform, with our law lambda, which is the uniform probability distribution. So this is very well known in, say, standard Borel sets. It's used to define probability measures, for example, in the category of quasi-Borel spaces. This axiom is very useful. It's rather intuitive as well, in a sense that sort of randomness should be sort of something that can be done kind of feasibly. If you like to think of it, the sample space is where all probability choices are being made. Perhaps God's there making the choices. Einstein said that God doesn't throw dice. Well, maybe he doesn't, but according to this, God tosses coins. So this is like the coin tossing measure of infinite sequences. So given this, I'm really going to flash this up. Regular conditional probabilities always exist for any pair of random variables. We have a converse, that is, we can go from a regular conditional probability given as a probability kernel to parameterized random variables. There's a generalization of the existence of independent random variables that uses conditional independence. Then I wanted to deal with stochastic processes. I was being very, very ambitious in my slides here. I just want to mention this point in that there's this nice book, Probability with Martingales by David Williams, in that he essentially tells you if you identify random variables up to almost sure equivalence, then you're doomed to be unable to deal with interesting stochastic processes on uncountable state spaces. Maybe that's true if one does probability theory in the standard way. If one does probability theory in this way, that's not the case, because in fact we can do stochastic processes. In the end, we see that random variables do not preserve arbitrary products. So just that's a categorical consequence of our axioms. I'll just mention that. I really don't have time to go through the details. We can deal with martingales, the Markov property. The definition of Brownian motion is just completely as you would read it in a textbook, but we can prove that Brownian motion exists from our axioms. Right, so we get to the end of the talk in 2 minutes. So one thing to say that I want to say now is we had this idea of implementing random variables as an abstract data type at the beginning. One nice thing is that we've seen the two equalities we've been using, the two equivalence relations we've been using are the ones that really make sense from a probabilistic perspective. So one is ordinary equality is just almost sure equality. That's good. But we've also got the equivalence relation equality in law. So of course, almost sure equality satisfies all the substitutivity laws one wants because it's equality. But equality in law actually satisfies a meta-theoretic substitutivity law, which is this, that in any of those settings you have, if you define it in the appropriate way, if you have a sentence, so that's something not depending on any assumptions, we don't have any free variables in it. If you have a sentence in the background set theory about a random variable A, about X, and you've got another random variable Y, then the sentence is preserved. Sorry, it's a predicate about random variables. Any property of random variables that doesn't require parameters is preserved under equality of probability law. And that's nice because it's a kind of a way of saying, though this is an axiom, but it holds in our model, it's kind of a way of saying that our axiomatization of random variables is sufficiently abstract. Or in homotopy type theory, I hope they don't mind me borrowing this, but in this terminology, in homotopy type theory, they talk about properties that sort of are dependent on actual equality rather than the right notion of equality, which is equivalence, as being evil. And in a sense, this is saying in our world, there is no evil. So I think that's a good place to end, because we're in a nice, happy world where there's a very happy God in the background tossing his coins and there is no evil. So here's some ongoing and future work, and I couldn't resist putting this last provocative line at the bottom. Okay, thank you very much. Sorry for a little bit overrunning, but we did have quite a few questions during the talk.
All right, let's thank everybody. Let's thank Alex for a wonderful talk. I think it was very interesting. And let's see if, feel free to ask any questions. If anybody has some.
Yeah, I have a question.
Yeah, Paolo.
So first of all, thanks a lot for the very nice talk. It's very interesting. So do you expect random variables to form a monad or a related construction in such a way that the law is a morphism of monads?
That's an excellent question. Where are the monads? So I do not believe that in my model that random variable is a monad. And I think it might actually be provable from the axioms that it can't be, but I haven't proved that. And there's an issue here to do with identifying random variables up to almost sure equivalence. That's one of the issues. To do all the probability theory I've looked at, I don't need it to be a monad. The functor of all probability measures on the power set is a monad, but I don't know if that's commutative. I don't know if you have a Fabini theorem here. Integration with respect to RV measures, that does satisfy the Fabini property. That's one reason for restricting to RV measures, but actually I don't know if my random variable measures form a monad. So here's a challenge. If one wants all nice things, including a monad, this is more to do with ignoring the random variables, but here's a challenge about going back to a convenient category for higher order probability theory. So it'd be nice to have a category for higher order probability theory that it has all these nice properties. And it's not known if quasi-Borel spaces have infinite product measures. So I have the first three, but I don't have I don't know if I've got the monad. They have everything except the infinite product measures.
Thank you so much. I have some ideas about this, but maybe let's talk about this offline. I want to leave room for more questions.
Right, so we actually have quite a few questions. I'm not sure if we'll be able to get through all of them, but let's start off with Malte Gerhold, who has a question.
Yeah, hi. So, hi. Thank you very much. Very, very nice, interesting talk.
Yeah,
so for me, it seems a bit scary that everything is built on this assumption, if I got it right, that there is no full axiom of choice. So do you see a chance maybe using outer measures or something else to get this nice setup with the equality of random variables and everything, where you in a setup which is compatible with the full axiom of choice, or is that?
Well, I think if you assume the full axiom of choice, there's no alternative but to have some notion of measurability in there too, because you're going to have to restrict your probabilities to something that's measurable. So my idea was to prove results of probability theory. It's better to avoid the measurability, to avoid the issues over measurability and give up on choice, which is, I mean, we've got countable dependent choice gets you quite a long way in terms of choice-like theorems that are actually relevant to the kinds of spaces that that are used in like the physical sciences and numerical mathematics and that kind of thing. So it's only if you get to very abstract sets that you're going to. But I mean, personally, I prefer to give up choice and just be able to have measures on arbitrary subsets.
Okay, thank you.
Great. So let's. So Dario Stein also has a question.
Hi, Alex.
Hi, Dario.
Have you been looking at random set-valued random variable or set-valued random variables? So taking values say in 2 to the r. Because I've been studying this in quasi-Borel spaces, and you have this really interesting phenomenon where essentially, if you can check if real numbers are equal, and if you can check if a set is empty, then you run into a contradiction with measurability.
Well, I don't run into contradictions. I'd be interested to hear what that is. Maybe we can take that offline. So in the treatment of stochastic processes, I'm looking at this random variables of functions here, which is so if you replace r with 2, then so I mean I'm essentially considering that sort of situation, and I'm dealing with it. Yes. So yes, I am considering that, and I think we could have a nice chat on Zulip about your issue and how things work in my setting, and I'd be interested to hear about that.
Yeah, that sounds great. Let's do that.
So I think we have time for one more question. I think Tom Leinster had a question.
Thank you. Thanks for a great talk, Alex. If we look at the slide you have up now, the first item is prove consistency of the axioms. You seem kind of intensely relaxed about the possibility that your axioms might be inconsistent. Can you say anything about your your intuition for why it shouldn't just all fall apart?
Because I've done almost all of it. So I mean, I've done enough of the calculations to reassure myself that the axioms are consistent. The only thing I don't know is I've got 2 versions of the model, one where I start off with Solovey's model of all sets are measurable, and the other where I start off with a construction, a topos in which everything is measurable but not Lebesgue measurable. The only thing I don't know is if the second topos satisfies my near-Borel axiom, which I'm hoping it does, because that would prove that it's weaker than the actual Lebesgue measurability axiom. But I am pretty relaxed about the consistency of the axioms because I've done I think I've basically done all the work. So,
okay.
But I haven't written it down as much. I mean, I haven't written it down or up. So,
right. Okay. Thanks.
All right. There is another question from Bas Spitters, but I don't know if we have enough time to address that at the moment because there's only about 1.5 minutes left, I think.
Yeah, probably not. I think we should probably swap, but I'd be happy to take Baz's question on Zulip.
Right. So let's thank Alex again.
Yeah, thank you.